everyone, today we will be discussing determinants. Before we jump into its explanation, I'd like to make a short announcement. We're now getting into complex mathematical topics. So from now onwards, I will help the viewers create a mental image of the topic we are discussing. Once a mental image is created, we can always use that understanding while coding, learning AI, etc. My aim is to help viewers use mathematics on a more day-to-day basis. By doing so, it'll help train our brains to make faster decisions. Who knows, we might end up being Sherlock Holmes performing 50,000 calculations in 1 second. Wouldn't that be interesting? I guess so. It has its pros and cons, but I think it's a handy tool. So let's start. So we'll start with the definition of determinant. First things first, what is a determinant? A determinant is a function which takes square matrices and then gives back a real number. So if a mental image has to be made for the word determinant, all you have to think is a box, alright, and this is some kind of a system or a function, because system is a function, or a machine. You can even call it a machine. So determinant is some kind of a machine which is taking input. Input is a square matrix and then produces a single number as output, which is real number. So this is all the image that you have to remember when you hear the word determinant. Alright, so what is a determinant? It is a function that takes a square matrix and then produces a real number outside. Alright, so that is the mental picture for this word, which is determinant, the computation that we perform. Now determinants follow certain properties. There are majorly four important properties. You might skip them altogether, it's not important, but if someone's studying determinants from an exam standpoint of view, that's why I've just put these 4 pointers together. Doing a row replacement on A does not change determinant of A. So if you're doing some kind of a row replacement operation on your matrix, then the determinant, the real number output, does not changes. Swapping two rows of a matrix multiplies the determinant by -1. So for instance, if you have first row as 1, 2, 3, and then the second row as 4, 5, 6, and then you swap these two rows together, so the determinant is actually multiplied by -1 in this case. Scaling a row of A by a scalar C multiplies the determinant by C. So let's say if I have a row, and then if I multiply this row with some scalar, any scalar value, so then my determinant also gets multiplied by the same scalar value. The determinant of the identity matrix IN is equal to 1. So the determinant of an identity matrix will always be 1. These are some of the important properties. I mean, you can literally skip them. Yeah, it doesn't have any practical application as such. Let us take an example now. If we are asked to find the determinant for a 2 cross 2 matrix, it's pretty simple. We just do a cross multiplication. This entry is first row, first column. This becomes A11. This entry is first row, second column. This becomes A12. This entry is second row, first column. This becomes A21. This entry is second row, second column. This becomes A22. And then the determinant of A is you just cross multiply. That is, cross multiply A11 with A22, subtract A12 with A21. So then 1 multiplied by 3 minus 0 multiplied by 0 is 3. This is how you solve a 2 cross 2 determinant. So the relationship that you can remember for a 2 cross 2 matrix is if you substitute the values with variables A, B, C, D. So AD minus BC is the determinant for a 2 cross 2 matrix. Now let us try to understand the implications of finding determinants when we have, let's say, 3 cross 3 matrices, 4 cross 4 matrices, and so on and so forth. Before we jump onto that, there's a quick recap I want us to do about upper triangular, lower triangular, and diagonal aspects of matrices. We've already discussed this in a matrices session, but I'll just do a quick recap here. So upper triangular is the case in the matrix when you have non-zero values on the upper side against the diagonal. So these are my diagonal entries, and on the upper side are having non-zero values, whereas the entries below the diagonal have zero values. Lower triangle is just the reverse. So in this case, this is the diagonal entries. The values below the diagonal are positive values, and then the other values are, they are non-zero values. They can be negative too at times. So non-zero values are on the lower hand side, and the diagonal entries, pretty much these are the diagonal entries. So these are the three things you have to keep in mind: upper triangular, lower triangular, and diagonal. Let's take an example in case of a matrix when we have all the zeros here, and this is my diagonal, and the positive values are on the upper hand side. So this is an upper triangular matrix, correct? So if you have a matrix in any of the triangular form, that is upper triangular, lower triangular, so all you have to do to find the determinant value is just see what are the diagonal entries and just multiply them together. So here 1, 4 and 6 are the diagonal entries, and then we just multiply them together to give a value of 24. And if A has 0 row or column, then determinant of A is 0. So if any of the row or any of the column in a matrix is 0, then the determinant itself becomes 0. You gotta keep this in mind as well. There's just some tricks for us to compute the determinant faster. Solving a 3x3 matrix for determinant, method 1. Now there are around 7 to 8 methods you can use to compute the determinants of a matrix. Alright. One is with minors and cofactors. That's what we are discussing here, but I'm not using the fancy terms because it's not required. But again, if you're viewing this video from an exam standpoint of view, so you might need those terms, and I'll be discussing them briefly here as well. There's a second method in which what you do is you take the values in the first column and the second column, and then you put it again and you do a diagonal multiplication. That is also a quick method, but I wouldn't really suggest that, because at times the multiplication of the values in the diagonal against very big matrices becomes a complex process. So that method's not the best thing to do. Then you also have row reduction methods and solving them by substituting linear equation values and then just bringing it to an independent values and then computing the determinant. But even those are slightly complex. So we're discussing the shortest and the simplest way to figure out how you can find a determinant of n cross n matrix. We're starting with 3 cross 3, but we'll jump into the bigger sections of matrices. So what do? Let's start with the trick, the simpler version first, without bringing the terminologies of minors and cofactors. This is my first row. You take out all the values which are there on the first row. So 2, 7, 4, just put them here, 2, 7, 4. Now the first entry, we'll take this as positive. The second will be negative, the third becomes positive. If it was a 4 cross 4 matrix, then you'll have to take next value as negative. So just alternate the positive negative signs depending upon what size of matrix you have. And then let's say if you've taken first row, in this case we have 2 as my first entry, so skip the entire column and then shift to the next column. Since we are taking the first row, so the entries that we're supposed to take is 1, 0, 3 and 1. So you multiply 2 with these 4 entries. Then we've taken the alternate sign, so it was a plus entry here, now it's a negative sign here, so this is negative 7, which is my second entry here. Again, we skip the entire column because this is the value we are taking, and we jump here. So we have 3 and 4 to take and 3 and 1 to take in this case. Again, we change the sign, which is plus 4 in this case, Then we have 3 and 4 and 1 and 0. Now we know how to compute determinant for a 2 cross 2 matrix. We do a cross multiplication. So 1 multiplied by 1 is 1, minus 0 multiplied by 3 is a 0, minus 7, 3 multiplied by 1 is 3, minus 4 multiplied by 3 is 12, plus 3 multiplied by 0 is 0, 4 multiplied by 1 is 4. And then we do the calculation, I don't have to explain that, and we get a value of 49. So this is how you compute the determinant of a 3 cross 3 matrix. I mean, the same strategy can be used for a 4 cross 4 matrix, but it will be a rigorous iteration, which we will discuss shortly. There's one quick thing, some terminologies that you can remember here if you're studying this from exam standpoint of view, and that is minors and cofactors. So minors this is how you perform it. What is the value here? This is first row, first column. This is M11, correct? This one is M12. This one is M13. This one is M21, M22, M23, and this one is M31, M32, and M33. So this is how we've represented them in the form of minors. Now the first calculation, oh, what just happened? Sorry, yeah. So the first calculation that we're supposed to do is for M11, which is minor against first row, first column, which is this entry, first row, first column. So you skip the entire column, and then you're skipping the row because the first entry is against the first row that we're supposed to take. The other entries are 1, 0, 3, 1. So for M11, how do you calculate it? This becomes, sorry about that, 1, 0 and 3, 1. Now we can compute the value of this minor here. 1 multiplied by 1 is 1, minus 3 multiplied by 0 is 0. So M11 becomes 1. Similarly, we can compute M12. M12 is what? It is first row, second column, which is 7 in this case. So we skip that, and the minor value here is 3, 4, 3, 1. You multiply 3 with 1, you multiplied 4 with 3 is 12. So it's 3 minus 12, it's minus 9 against this entry. Similarly, you can find the minor for M13. Let's try finding the minor of M21 in this case. So M21 is second row, first column, which is this. Since we are taking this row, so then the entries that we're supposed to take is 7041 for M21. For M21, it is 7, 4 and 0, 1. Why? Because this is the entry. So we're skipping this row, and then we have to take all the values of the adjacent columns in this case. So it's 7, 4, 0, 1. Similarly, we will have to find the minor of M31 and then put in the values and then compute the determinants. Now what we have to do additional step here is, if the addition of these two numbers is a positive value, the computation value doesn't change. So for instance, we had a value of 1 here, right? For M11, 1 multiplied by 1 minus 0 multiplied by 3 was a 0, so it was a 1 here. Since 1 plus 1 is 2 is an even number, we don't have to change the sign. However, 1 plus 2, 3 is an odd number, so we'll have to change the sign here. So minus 9 will become plus 9 when we are trying to find the cofactor. So once you've found the minors, you're supposed to compute the cofactors by changing the sign depending upon the addition of these two values, and then you are supposed to calculate and find the determinant value. Alright, so that's just the terminology that you have to keep in mind. And even if you want to skip the nomenclature of the terminology, you can just simply remember this. Pick up the first row, remove those values, alternate the sign, so plus minus plus minus plus minus depending upon the size of your matrix, and then just pick up the value of, so for instance, I just explained it, I'm doing a quick re-explanation here. So in this case we had 2 on my first row, so I took my first row entry, and then since it's in the first column, so you're supposed to skip the entire column, and then it's 1301, and then it's a negative sign here because there was a positive here, and then again 3431 plus 43410 because you're going to skip the entire column. That's pretty much it. I mean, that's all you need to remember when you are trying to compute the determinant. For a 4x4 matrix, again, let's apply the same logic. Stick the entries, all the values in the first row outside. So we have 2, 7, 4, and 1. Let's switch, alternate the sign. We start with positive. So this is positive, this is negative, this is positive, and this is negative. So it's 2, minus 7, 4, and minus 1. So now when we are taking the first value, it's in the first column. So I'm supposed to switch my column. So for my first entry, the values become 104, 312, 611. Now it's a negative sign. We've alternated the sign. We've changed the sign. So this becomes minus 7. And then it's the second column. So we're supposed to skip the entire column. Then we have these 3 columns left, which is 345, 312, 611. And it becomes plus 4. Then we can skip the entire column, and then we have 345, 104, 611, 345, 104, 611. Again, alternate sign, negative 1. This column is consumed, so will be 345, 104, 312. So this is how you find the determinant for a 4x4 matrix. And now, I mean, this is obviously not the complete solution, because now we have a 3x3 matrix, and then again you're supposed to, take the entries against the first row and then take them out, solve the 2x2 matrix, and then plug in the value. So it's like we're doing a recursion against the matrices to find the final output in this case. Alright, so that is how you solve a 4x4 matrix. And then let's say if you're trying to solve a 5x5 matrix, that's how we're going to be solving it. So I think that's pretty simple and straightforward. For matrices, we're just doing a recursive call over and over until we reach to a point that the matrix is 2x2, and we can always cross multiply that and then solve it other way around. So from once we've reduced the matrix from 4x4 to 3x3, then we bring it down to 2x2, and then we solve it completely. So this is pretty much it that that you'll ever need to know against determinants. It's just one quick thing I want to add here. We didn't discuss why we should know determinants in the first place. So determinants are quite handy when you're supposed to find volumes and areas of triangles and parallelograms. But in computer visions and AI problems specifically, determinants is really handy, because when you are giving a function that is a determinant, in this case a square matrix, and then you're just getting one single value back. So it's like, the whole information which was stored inside the matrix is put in one single real number. So you get a mental visual picture of what exactly the kind of data or information is being stored in that matrix by computing the determinant for the matrix and then just seeing a single value. So that is the beauty of determinants. Like, it takes all the complex matrix information, storing different gradients, patterns, could be image data, could be anything, could just be variables and things like that, and then just gives you a single one real number as an output. So you can study, visualize, create patterns, plot those, and then understand what kind of a metadata information was actually stored in matrix. When we will solve computer vision problems or AI problems, I will get back to the importance of determinants, and this concept will come more handy there, because we will be using predefined functions to compute determinants for matrices. So just keep in mind what exactly a determinant is, which we discussed. It's a function, takes in a square matrix, and then gives a real number as output. So just create this mental picture in headspace. As soon as you hear the word determinant, you're supposed to close your eyes, think there's a square matrix n cross n which has equal number of rows and columns, and then you're putting it inside some kind of a machine which is a determinant. It does computation on that and then gives you just one single number back as the output. That's all, right? This is the mental picture. If you have any questions about anything in matrices or determinants in this session, just write them down in the comment section and I will revert you back. And yeah, I think that's pretty much it for this session. Thank you.